Thank you very much. Many thanks to the organizers for giving me the opportunity to join this great event. So yes, what I'm going to discuss today is a series of joint works with Daniele Celoria and Carlo Collari. And I'm going to talk about, let's say, plenty about überhomology today, a tiny bit less about double homology of moment-angle complexes. So I apologize in advance for that. But so before I start, I wanted to say at least a few words about the motivation, about the motivations that led us to study this homology theory. And the very first is about minima triangulations of manifolds. So the idea was at least to have some homological invariant that could detect minima triangulations of manifolds indeed. So the second motivation comes, I would say, from applied topology. So as you might be aware of, nowadays we have this new trend of topological data analysis with applications to various fields. And the idea is to associate to data a family of graphs, and in particular persistent homology. But in some cases, it's also important to introduce new invariants of graphs. And this is also part of the motivation. But the third one, which is the, let's say, understanding the Mayer-Vittori spectral sequence, I think it's at least my main motivation. And you might be aware of the fact that if you start with a simplicial complex and you consider a good cover associated to it by the nerve lemma, then you get an homotopy equivalence between the simplicial complex and the nerve of the good cover itself. This uses the Mayer-Vittori spectral sequence, in particular the fact that for good covers, the second page of the spectral sequence is quite simple. So it's everything is encoded in one line. So the relation is pretty straightforward. But the question, what happens for non-good covers, for bad covers, is still there. And what sort of combinatorial topological invariants does the Mayer-Vittori spectral sequence contain? This is a bit more obscure. And this is, I think, one of at least my main motivation. So if you get bored, so what I'd like that you remember today is the following facts. So the first is that überhomology is a triply graded homology theory for simplicial complexes. As I was mentioning, this was introduced by Daniele Celoria, and its definition uses a poset homology theory, which is basically the Kovanov homology, a Kovanov-like poset homology theory. And Kovanov, to study basically knots, to define the homology, Kovanov homology, what does it do? So it starts with a knot, it considers the Boolean poset of all possible resolutions of the knot, and then it twists this Boolean poset with a functor, and then it computes the basically Kovanov homology groups. We're going to do something similar there as well. And the third thing is that this überhomology is related to some combinatorial quantities, namely the connected domination, connecting dominating sets in a graph. It is related to the Mayer-Vittori spectral sequence. This was one of the main motivations. And it is related also to the double homology of moment-angle complexes. So let me start with some framework. So first, for us, all simplicial complexes are going to be, for today, finite and connected. And let's assume that our vertices are going to be M, let's say V1 to Vm. And the bicoloring on K is simply a map from the vertices to 0, 1. We only color the vertices of our simplicial complex. We do not color the edges, or we do not assume any relation on the edges or the agency relations between the vertices. So it's just a map on the vertices, 0 to 1. Now, if we have a bicolored simplicial complex, what we can introduce is the weight of a simplex. So let's say that the simplex has n+1 vertices. So its epsilon weight is going to be n+1 minus the number of one-colored vertices. So the weight of sigma is simply the number of zero-colored vertices by epsilon. So this is going to give us a snapshot of our simplicial complex. Once we have a weight, what shall we do? We just consider the filtration on the simplicial chains of our simplicial complex. But what I want to observe here is that the simplicial differential splits in two parts. The horizontal part is the one that preserves the weights of the simplices, and the other side is the one that decreases the weight by 1. So we get rid of the delta D. We only consider the horizontal part of this differential. And in this way, we got a bigraded chain complex, which is bigraded by the simplicial dimension and the weight dimension. The differential we use is the horizontal differential. We can compute the homology. Let's call it horizontal homology. I'm going to give you a straightforward example here, just to have at least the same conventions. So let's start, for example, with the 2 simplex over there. We have, let's say, 3 vertices, V1, V2, V3. V1 is 1 colored, whereas V2 and V3 are colored with 0. So on the top right, we can see here the bigraded decomposition of the simplices of delta 2. For example, F sits in by degree 2, 2. This is a 2 simplex, and it has 2 0-colored vertices, whereas, let's say, V1, this is a 0 simplex, is 1 colored, so this sits in by degree 0, 0. And here the simplicial differential splits in the 2 parts, so the horizontal part that preserves the weight, and the other side. So the horizontal homology is the one on the bottom left, and as we can see from this picture, the horizontal homology with respect to this bicoloring is going to be generated just by V1 in by degree 0, 0. All the rest is vanishing. I see. Yeah. Okay. Yes, this is to remind me that so we can have so the epsilon weight measures the number of 0-colored vertices in a simplex, and the horizontal homology is bigraded by the simplicial differential and the weight. But the 0 weight part of the horizontal homology is quite simple. This is actually the simplicial homology of the 1-colored subcomplex that we're considering. So let me give a couple of examples more of what can happen there. So let me start with the extreme case in which all vertices of our simplicial complex are 0-colored. So in this case, well, our simplicial differential has to forget at least one of the entries of our simplicial complex. So the horizontal differential is 0, because we cannot preserve the number of 0-colored vertices. So the horizontal homology is actually computing the number of simplices in our simplicial complex, nothing more. On the other hand, if you color everything with 1, what happens is that the simplicial homology and the horizontal homology agree, because we do not have 0-colored vertices, so the differentials are the same. And more generally, as I was saying, the 0-weight degree part of horizontal homology looks at the simplicial homology of the 1-colored subcomplex. This is going to be important. And here, for example, there is another delta 1 colored with 2 vertices, 0 and 1, then again is generated in by degree 0, 0, but just one single vertex. Any questions so far? No. If everything is right, then the main question that I here have is that if we start with just a bicoloring, we are only looking at a subcomplex, basically, of our simplicial complex. But we want to, how do we choose, like which coloring, how do we choose the coloring that gives us the preferred subcomplex? So there's no way. I might choose epsilon, you might choose epsilon prime, but we want to put all this together. And this is where the Kovanov-like homology comes in. We want to pack all this information in one single object. What do I mean by this? Before getting to the definition, let me just observe that if you have 2 bicolorings, epsilon and epsilon prime, which differ at a single vertex vi, so let's say that epsilon vi is 0, epsilon prime of vi is 1, then what you can consider is this map on the level of chains that associates to a simplex sigma, the simplex itself if the weight is preserved. So if the epsilon weight of sigma and the epsilon prime weight of sigma are the same. Otherwise, we put it just 0. And as you can see, there is a sign there, and this is there because we want to use these maps to define a differential. So let me rephrase everything one more time. So if we consider the set of all possible bicolorings on our simplicial complex, this gives us the structure of a Boolean poset on the number of vertices of the simplicial complex. And for each bicoloring epsilon, we are associating the bigraded horizontal homology of K with respect to this bicoloring. And if we have a covering relation between epsilon and epsilon prime, we get also a map on the level of horizontal homologies. So we have a functor from the Boolean poset, can be seen as a category, to the category of bigraded modules over the base ground ring. And for a given poset P seen as a category and a functor F, what we can do is to construct this Kovanov-like poset homology. This was also used by Turner and Wagner, by Chandler, myself with some other collaborators, Collari and Ditrani, to be fair. And if you are familiar also with functor cohomology, what you could do is also consider the functor cohomology now of the Boolean poset with respect to this functor. Kovanov homology is slightly different, but the two agree basically everywhere, but in the degree 0 and 1. So basically, we can think about functor cohomology. And here comes the definition. So the human homology of K is the triply graded homology theory of the Boolean poset of all bicolors of K with coefficients in the horizontal homology of K itself. Let me be a bit more concrete. So for each K, we consider as J chains, überhomological chains, the directed sum of all possible epsilon of length J of the horizontal homology of K. And by length of epsilon, I mean the number of one-colored vertices in epsilon. The differential is the sum of the differentials over there, but in order to be more illustrative, let's look at this diagram. This is a Boolean poset associated to all the possible bicolorings of a simplicial complex with 3 vertices. And the Boolean poset is ranked by the number of one-colored vertices. So we start from the totally 0 colored simplicial complex, and by coloring one by one all the vertices, we end up to the totally colored one simplicial complex. And for each column, as you can see, we decorate the Boolean poset with the horizontal homology with respect to the epsilon colorings. We take the directed sums, and as we use the sum of the differentials to construct actually the differential between the überhomological chains. Okay, this is a lemma. You got a cochain complex whose homology is überhomology. And it's triply graded because we now have the überhomological degree, we have the simplicial degree, and the weight degree. The horizontal homology was bigraded. Let me give a few computations to, let's say, to put our hands on this theory. So first, let's start with a standard simplex. What do we get? At the level 0, so for the überhomology in degree 0, we got this sum of copies of Z with the power n plus 1 choose K plus 1. This is the number of simplices in K. And for J equals 1, instead, we have a copy of Z, and this is generated by the sum of all vertices in the standard simplex. This is slightly different to what we might expect. And if we consider the boundary of the standard simplex, what do we get? Again, in a level J equals 0, we get something that's related to the number of simplices of the simplicial complex. And on the level in between 0 and n plus 1, now we get some non-trivial homology groups. In particular, for J equals n plus 1, we get a copy of Z, and this is generated by the fundamental class of the sphere. This is actually a theorem proved by Daniele Celoria, and it says that if K is a triangulation of a closed-end manifolds, then in the top degree we find the fundamental class, and this generates the Z in the triple degree Mn0, or whatever, in the top degree. So on the bottom, so on the top we have the topology of K as we go from the zero colored simplices to the one colored simplices. On the top degree, we find some topology. On the bottom, there is something related to the combinatorics of the simplex, of the simplicial complex. But this is also a theorem. And in fact, we have that in the überhomology in degree 0 of the simplicial complex K, this is given by this directed sum of z to the power nj, where nj is the number of j-dimensional simplices in the intersection of all closed stars of the simplicial complex. So it's really a combinatorial quantity. And in particular, if you start with the simplicial complex, which is not the standard simplex, but you take the barycentric subdivision of it, then this intersection of the stars is going to be, well, empty. So the überhomology in degree 0 vanishes. And this is also the relation with the, at least with some relation to the stellar subdivisions or to the triangulations of manifolds that I was mentioning at the very beginning. So some other results in this direction. For example, if K is connected and the diameter again is bigger than 3, then again the überhomology vanishes. This is, let's say, these were a few examples. We have learned that in the top degree we found some topology, in the bottom degree we found some combinatorics, but I want to say a bit more of what we managed to prove. And in particular, instead of focusing on the whole picture, let us restrict first to the case of the weight degree equals to 0. Remember, we have 3 degrees. We first restrict to 0 the weight degree 0, and then we restrict to the simplicial degree 0. So we have a singly graded homology theory. But this is associated to simplicial complexes. The simplicial degree is 0, so it only depends on the one skeleton of these simplicial complexes. So this is an homology theory of graphs. Let's call it Bode homology. And as I was mentioning at the very beginning, this is related to connected dominating sets in a graph. I assume, so let me remind what a connected dominating set is. If G is a graph, and we take a subset of the vertices of G, then we say that S is connected if it spans a connected subgraph of G. And we say that's dominating if each vertex of G is 1 close to S, which means that basically each vertex of G either is in S or there exists an edge that connects this vertex to a vertex in S. The connected domination polynomial is given by the sum of all possible connected dominating sets and of T to the power cardinality of these subsets. And what we proved is that the Bode homology is actually a categorification of the connected domination polynomial at -1, which means that this Bode homology is functorial with respect to some a certain category of graphs, and its Euler characteristic is given precisely by the evaluation of the connected domination polynomial at -1. So we actually proved something stronger, the fact that the chains Bode homology actually retract onto the subcomplex generated by the connected dominating sets. So which means that at this level, really what we're seeing is a truly combinatorial quantity given by these connected dominating sets. And this is quite important also because these sets are related to some network theory, are important in some context, also in computer science. So let me give you some few computations to also have an idea of what we are computing here. So for example, if G is simple, then the first Bode homology group is non-trivial if and only if this was the complete graph. So which means that can detect the complete graph, a single degree is enough. And if G was a disjoint union of 2 graphs, or if G was contractible, or if there's a leaf, then we have a vanishing result, everything is trivial. It is well behaved with respect to cones of graphs, but in particular, if you start with a cycle, what you get is the, up to shift, the reduced homology of S1. So it's not, so it is combinatorially, but there is also a tiny bit of topology hidden there. And the question, where does it sit? The answer is given by the Mayer-Vettori spectral sequence. So some of you might already know what I'm going to say here, but let me just say that instead of restricting now to the singly graded Bode homology theory, just let's consider the k equals 0 part of überhomology, which means we restrict to the 0 weight degree of überhomology. Just remember that the horizontal homology of in weight degree 0 captures the simplicial homology of the one-colored sum complex. So if we restrict to this, we got a bigraded homology theory. And in order to analyze it, let's consider the anti-star of vertices. By this I mean, so if Vi is our vertex in the simplicial complex, what we can consider is the induced subcomplex by all vertices in K but Vi. So if your K now is not the standard simplex, and you take the anti-star of each vertex in your simplicial complex, what you get is a cover of the simplicial complex, and you can run the Mayer-Vettori spectral sequence. Actually, here, instead of running the Mayer-Vettori spectral sequence, we consider the augmented Mayer-Vettori spectral sequence. And augmented means that we also consider the empty intersection. So the homology of K is also there in the picture. And the result is that there is an isomorphism between this 0 weight degree part of überhomology and the second page of the augmented Mayer-Vettori spectral sequence. So the degree, there is a shift of degree, but yes, and this is for all simplicial complex, but the standard simplex. Of course, the standard simplex plays a big role now because, well, we do not get a cover by using the anti-stars. What's the proof? Yeah, well, basically, this is the proof. So what it does say. So if you remember the definition of the überhomology, what we were considering was the Boolean poset of all possible bicolorings on K. And at each column, we were computing the horizontal homology of with respect to the coloring epsilon. But as we are focusing, we are restricting to the 0 weight degree part, this horizontal homology is the simplicial homology of the induced part, of the one-colored part. But the one-colored part can also be interpreted as the intersection of the anti-stars of vertices in the 0-colored parts. So there is this duality. I need to reverse the arrows. But now if we take the directed sums of everything column-wise, what we get there is the Q line in the first page of the spectral sequence. If we turn the page, we get the isomorphism. So the proof is quite direct. Let me give some consequences of this fact. First is that this bigraded, the 0 part, let's say, of überhomology is non-trivial if and only if K is the standard simplex. So which means that the Bode homology was detecting the complete graphs. The relation that we say the topology was there via the spectral sequence, the second page of the spectral sequence. So it's now clear that we got also the standard, we detect also the standard simplex. If the anti-star cover is one array, now we get a relationship between the Euler characteristic of K and the connected domination polynomial -1 of the one skeleton. And this is again by the spectral sequence argument. And between the others, for example, we have again that's well behaved with respect to cone operations and the likes. This was everything basically for überhomology in the lower weight degree 0, but we have no idea of what happens in the higher degrees. This is still open, and yeah, if you have any ideas in this regard, so please do tell. And now it comes to the relationship with double homology. Double homology is an homology associated to the homology of moment-angle complexes. Likely, I do not have to explain. We have learned pretty much a lot about the moment-angle complexes this week. And let me just say that, sorry for the technical slide, but this is to be precise. So the homology of the moment-angle complex can be decomposed as the reduced homology of the induced subcomplexes of K itself. So I is a subset of vertices of K. What we can consider here is the inclusions of Ki into Ki unions J, where J does not belong to I. This gives us maps in a level of homology, and we can define this differential delta prime, which was shown to be actually to square to 0. And associated to the homology of the moment angle complex, we can consider the following: a bigraded decomposition with, using this H minus K to alpha K, and the differential just defined induces preserves this bigraded decomposition, and it was defined by Limonchenko, Panov, Song, and Stanley, this the double homology of the moment angle complex as the bigraded homology of this chain complex with respect to this differential. I do not have time, unfortunately, to look more into this theory, but what I wish to say is that the zero weight degree parts of überhomology and double homology share many common properties. For example, besides the fact of being bigraded and to be induced by subcomplexes, they both capture the fundamental class of our simple complexes. They are well behaved under cone suspensions or with respect to chordal graphs. They detect the standard simplices. So a relation between the two ought to be there, and the relation between the two is given by the Mayer-Vettori spectral sequence. The theorem, it says that the double homology in by degree minus K to L and the überhomology in by degree L minus K minus 1 L are isomorphic, but this happens to be only in a degree L minus K, not 0, 1. Why is that true? Because if we consider the the Mayer-Vettori spectral sequence associated to those, on one side, the double homology side, we need to consider the augmented reduced Mayer-Vettori spectral sequence. On the überhomology level, we need to consider the augmented Mayer-Vettori spectral sequence. So the difference between the two is just that we're considering the reduced homology rather than the unreduced homology. We know that the two are pretty much related, but this is the reason why the isomorphism happens to be only for L minus K, not 0 or 1. But also for these lower degrees, we do have a relation between the two. And this is pretty much what I wanted to say. And I thank you all with the picture given to me by Daniela. Thanks.